Hello everyone, in this project we are going to tackle the power system problem peak shaving using diesel generator. So in this video, in start I will explain what's the problem we are facing, and then using this MATLAB code I will explain how I address the problem and solve it using this MATLAB program. So let's first understand what's the problem. So imagine we have a city or we have an area where we are supplying our power using a main substation. So here you can see from this is the 24 hours chart, and on y-axis we have the power supply, or we have our load in megawatts. So imagine during the day our power usage is low, and when in the evening everyone is going to home, turn on their ACs, appliances, so there is a peak, there is a higher load demand, which you can see right over here in the dotted lines. So this is the peak demand at these hours, and there is another peak which is a small peak, which is from 8 to 10 hours. This is this small peak demand in load, and in the other part of the chart we have our load demand less than the grid limit. So our grid limit right over here in this chart is 2.5 megawatt. So during the day or during these hours, our demand is less than our grid limit. So we are good to go. But when from 8 to 10 hours, or from 15 to 22 hours, we have a spike in demand, we have more power demand than our grid limits. So in that case, we may blow up our transformer, our lines, or we may even face massive penalties. So at these points, these hours, we are going to introduce 3 diesel generators to address this issue which we are facing in form of higher load demand. So right now in this code, the 3 diesel generators which are located at 18, 24 and 30 are fixed at these locations. No optical location for these diesel generators. These are fixed, but we may consider another MATLAB program where we can find the optimal location of these diesel generators. But right now these are fixed. But the size or the load which they have to provide uh, to the line, this is actually find by the MATLAB program, which I will show you later in the programming section. So we use a built-in program which I will explain later. So let's first we have here our load demand, and here the different charts, right? If I explain this, at the 18 hour we have our 3 diesel generators, 18, 24, 30. All 3 diesel generators are going to supply power, and right over here you can see at the 8th hour our 2 generators. First one is 30 DG30, this one is supplying power, and the red one DG24 is also supplying power. And at the rest of the hours, our load is under grid limit, and no supply and no power is considered from the diesel generators. So in rest of the hours our diesel generators are turned off, and we are saving our cost, or we are saving our fuel cost. So that's how this optimally works together. And if we saw here in the figure 3, which is about the minimum bus voltage. So the here we have mark our dotted line with the 0 0.9. This is in per unit. So this is a line which we have draw. So the voltage fluctuates above, but stays safely between the 0.93. This is the around 0.94 to 0.97. So this confirms that the solution which we have provided in form of diesel generators, uh, it's not just financially cheap, it's also it have physically safe, that our voltage limits are within the range. And let me show you another perspective here. I think so this one is the 19 hour. So this is the 19 hour. At the 19 hour we have load demand of around 3.715, which you can also see here, 3.715 at the 19 hours. Our load demand is this one, but we are taking the power from the grid is 2.488, as our grid limit is 2.5, and the rest of the power we are taking from the diesel generators, which is 1.315. So at the 19 hour, all our three diesel generators provide us the output, provide us the power, and if we sum the power of these three diesel generators, here is the uh, value in megawatt, which is 1.315. So now let's switch to the programming part. So let's start with the MATLAB files. First one is the IEEE 33 bus system. I will not spend much time there. So here we have line and load data and resistance, reactance, and bus numbers. All that stuff is just written here. And in the next program, run radial power flow. So in this file, we have utilized the backward forward sweep load flow program. And in the start of the program, we have converted just our line and load data into the per unit. So why per unit? Because our load is in megawatt, and our resistance reactance is considered in ohm. So if we put that stuff directly into the program, that will become a mess. So that's why we have converted all the parameters uh, into the per unit base system. Maybe um, you can change the specification if you have a different network right over here. And then we have run our load flow program, and at the end of this program we have calculated our total losses and the branch losses. So at the end of this program we have just sum up each and everything. And here is the main function file. So this is the main program. So in the start of program we have just initialized the load profile for each hour. We have mentioned the load profile. So 1.0 right over here mentions that we are considering the full load at that hour, and if we have 0.4 means we are just considering the 40% load at that bus. And next we have DG specs. So this is the here we have mentioned the location of the diesel generators. This is the minimum and maximum power that can deliver, and here are ABC. These are the cost coefficients for diesel generators. There is a proper formulation for that, and based on that we have set these parameters. And next one we are just considering the constraint parts. So if I show you here that the grid limit we have set to 2.5, you may change that factor if you want. And next here we have not used any kind of optimization algorithm. We have utilized this quadprog, which is built-in MATLAB function, which act as optimization algorithm or a solver which solve our problem by considering all that stuff. And here H and F parameters, which are actually the cost of the fuel, A and B underscore INEQ, these are actually mention the constraints, and LB and UB lower bound, upper bound are the generator size limits. So the next one, uh, here this is the file where we are considering the quadprog optimization. And if I show you here, next one is where is that file? So here if I show you that this factor, this is the reactive support. Generators not actually provide active powers, they are also provides the reactive power. So considering a power factor, so this is the factor, we are injecting both real and reactive powers into it, and then we are run radial power flow addressing this file, which file calculate the load flow program for all the data which we have provided above, and here are the mention of the results, and here is all that stuff. So that's how it work. Hopefully you understand the issue, and if you have any issue or any query, you may ask in the comment section. Thanks for watching.